So we're very happy to have Ozgur Bayindir, and he will be telling us about algebraic K-theory of THH of FP.
Okay, thank you very much for having me in your seminars. It's great to see you and meet you. This is a joint work with Tassos Molinos that I'm going to talk about. The title Algebraic K-theory of THH-FP. That's our main result. So the main result of this work is the computation of the algebraic K-theory groups of THH-FP. And I'll try to get into, so in order to prove this result along the way, we also provide a new identification of THH-FP as an E2 algebra. So that's something we believe to be of interest on its own, because THH-FP is a pretty fundamental object in trace methods. And it's also something that we proved in order to aid our computations. So I'll start my talk with a quick background on algebraic K-theory with a few applications of algebraic K-theory. This part of the talk will be pretty, it will be, the goal of that, this first part of the talk is to provide the motivation for algebraic K-theory. And this part of the talk, I will be a little vague and fast. I will not make everything very precise, because those are not things I'm going to use later. Those are more of like a philosophical motivation for what's coming next. But and then I'm going to talk about trace methods for algebraic K-theory, where I'll be more detailed. The trace methods for algebraic K-theory, that's a program that was developed to provide computational tools for algebraic K-theory. In particular, I'm going to talk about the recent Nicolas-Schosse approach in as much as detail as I can, this is a new work that simplified algebraic K-theory computations, in particular the computations that are done using trace methods. And then if time permits, I'm going to, that time will permit this part. I'm going to mention our main results and say a few things about their application. And then if time permits, I will say a few things about the proof of the main result. Okay, so I'll start with the definition of the degree 0 K-theory groups of a ring. That's due to Grothendieck. So if you have a ring, let PR be the monoid of isomorphism classes of finitely generated projective R modules. Okay, so you look at finitely generated projective R modules, and under direct sum of finitely generated projective R modules, this is a monoid. And any monoid, you can formally group complete a monoid, and the group completion of this monoid is called the K-theory group, degree 0 K-theory group of R, and this definition is due to Grothendieck. So to clarify what I'm saying here, let's say if we have a field, right? If R is a field, then finitely generated projective R modules are precisely finite dimensional K vector spaces, and these are classified by their dimension, obviously. So PK is precisely the natural numbers, right? And direct sum corresponds to addition of dimensions, so you get the natural numbers. Group complete that, what you get is integers. So voila, we proved that K0 of a field is integers. So hopefully this clarifies the definition. Later, there is the definition of Whitehead and Boss in 1950s of the first algebraic K-theory group. So it is defined to be the abelianization of the infinite general linear group on R. The intuition for this comes from the definition of first topological K-theory of a space. So that is defined using vector bundles on the suspension of a space, right? And then the gluing maps defining the vector bundle intuitively translates into this infinite general linear group abelianization. And that's where the intuition for this comes from, by looking at that K1 groups of topological spaces, its suspension spectrum, etc. And the big application for this result is the S-cobordism theorem. It says that if you have a closed manifold dimension larger than or equal to 5, then this K1 group, this quotient of the K1 group, here, what you have here is the group ring of the fundamental group of M, right? You take the K1 of that and you quotient out by the units of the group ring, which sits inside here, right? So this contains obstructions to triviality of what's called H cobordisms on M. So an H cobordism is a cobordism where inclusion of the boundary maps are homotopy equivalences. And you say an H cobordism is trivial if it is equivalent to a cylinder, basically, if a H cobordism is equivalent to a cylinder. So this is pretty interesting because it is saying that this thing that we define in a completely algebraic manner ends up containing obstructions to this topological phenomena. And then there's the later definition of Milner's definition of second K-theory groups. In 1967, the application was actually to number theory arithmetics. I will not get into that. But the thing is that after that point, people started looking for definition of higher algebraic K-theory groups, which will give you a full homology theory for rings. In particular, if you have, for instance, an ideal of your ring R. I mean, what would you expect for what would you expect for such a homology theory on R, right? First of all, you would want it to agree with the existing definition of lower algebraic K-theory groups, and then you, for instance, one thing you would want it to do if you have an ideal of your ring R, you would want to have these relative K-theory groups to be defined, which fits into a long exact sequence of this form, right? So you would want such properties to be satisfied by your higher algebraic K-theory groups. So this was an open question, and actually Milner defined his notion of higher algebraic K-theory groups, but actually it didn't do what people wanted to do. It became apparent after a while that it was not the correct definition. And then later it's due to Cullen that we have the correct definition, what is accepted still today as the correct definition of a higher algebraic K-theory groups. It is saying that if you have, so the definition of Cullen is given in the following way. If you have a ring R, then you look at the space, and then its homotopy groups become your degree n algebraic K-theory groups, and the space is, again, it's defined using the infinite general linear group. The thing is that you take the classifying space of this group, right? And then you apply what's called the plus construction. This is a construction that basically kills a maximal perfect subgroup of pi1 while keeping homology the same. It's an interesting construction. And this space turns out to contain the correct information for your K-theory. So this is still accepted as the correct definitions. There are alternative definitions for more general situations, but they all boil down to the same thing for rings. And then later Cullen computes the higher algebraic K-theory groups of finite fields. It's for a field of degree Q. I show the result here. And actually, Cullen wins the Fields Medal for his definition and for his computations, for his algebraic K-theory computations. But the interesting thing is that, for instance, the methods that are used for the computation of these groups turned out to be pretty difficult to generalize to different situations. They were only working for these very specific cases. For example, Quillen also tries to compute the algebraic K-theory groups of quotients of integers with prime powers, which, you know, if you look at this ring, it's a pretty innocent looking ring that, you know, one could guess that it would be possible to compute these algebraic K-theory groups, but actually Quillen fails to compute these, and this is actually still an open problem in algebraic K-theory. So these algebraic K-theory groups turn out to be pretty difficult to compute. Another interesting connection of algebraic K-theory, both an application and an evidence of the difficulty of algebraic K-theory computations, is the connection of algebraic K-theory with what's called Van de Waal conjecture. So I'll not get into details of this, but this is a conjecture in arithmetics. It's a heavily studied important conjecture that is still open. And if you look at the description of this conjecture, it doesn't look like it has anything to do with homotopy theory, but it turns out to be equivalent to this question in algebraic K-theory. So it's pretty interesting that we have this connection, but it's also showing that actually computing these algebraic K-theory groups may be pretty difficult. So I gave you the definition of algebraic K-theory of rings. There are other definitions out there which allow you to define algebraic K-theory in more general situation. For example, there's what's called the Walthausen S construction, which allows you to compute the algebraic K-theory of what is called Walthausen categories. These are categories with the notion of a cofibration and weak equivalence, of course satisfying some axioms. For instance, this allows you to define algebraic K-theory for things such as pointed model categories, topological spaces, ring spectra. Ring spectra is something I'm going to talk a little bit about in a second. But so for all these things, now we can easily talk about. We have the definition of algebraic K-theory. In particular, our project concerns algebraic K-theory of ring spectra, and in particular, trace methods often concern is about algebraic K-theory of ring spectra. Okay, so for those who haven't seen much about spectra in a long time, I will try to do a very fast, reminder about spectra and a few things I use about spectra. So one can think about the category of spectra as a category obtained from topological spaces by inverting the suspension endofunctor on topological spaces, right? If you have a space, you can take its suspension, so there's that endofunctor on topological spaces, but this is not really invertible. So it's the idea is to formally invert this functor, and you obtain this new category. Vaguely speaking, that's how you obtain spectra. And the idea is that there are many reasons to do this. The idea is that once you do this, you still preserve a lot of complexity of topological spaces in spectra. But in the meantime, category of spectra, although it contains a lot of complexity from topological spaces, happens to be and has to be more approachable and more algebraic, in particular better suited for computations. We can easily say spectra is the main setting for stable homotopy theory. That's where that's the setting one works in very often while doing stable homotopy theory. So I was just saying that spectra gets you closer to algebra from topological spaces. For instance, there is this notion of fiber sequences in spectra, which generalize the notion of short exact sequences of, for example, chain complexes or modules. In particular, it makes the homotopy category of spectra a triangulated category. So it's somehow like in a categorical sense, you're getting closer to algebra by going from topological spaces to spectra. For example, spectra linearizes topological spaces in the sense that mapping homotopy class of maps between two spectra is an abelian group in a canonical way. And in particular, for each spectrum, we have a notion of a homotopy group, which is defined for each integer. So you have non-negative homotopy groups as well as negative homotopy groups, and these are all abelian groups. So for instance, I mean, for a topological space, you don't have the negative homotopy groups, and at the same time, pi 0, pi 1 may not be abelian groups, right? But in spectra, things are nicer in general. And one thing to keep in mind is that, again, in the general case of a ring spectrum topological space, again, I'm going to define ring spectrum in a second, but in all these situations where we can talk about algebraic K-theory, what we do is that actually we talk about an algebraic K-theory spectrum, and then the homotopy groups of that spectrum become your algebraic K-theory groups. So this allows you to think of algebraic K-theory as this object with topological structure rather than just these abelian groups, right? We think of algebraic K-theory as an object with more structure than just these abelian groups that we assign to X. Okay, so I was saying spectra is well suited for these algebraic constructions. This and an important structure on the category of spectra we use for that is the fact that it's a symmetric monoidal category. If you choose a nice model of spectra, then it's a symmetric monoidal category, and the monoidal product is denoted by the smash product. So it is saying this is something that comes from topological spaces, smash product of topological spaces, really. It's constructed using that. And it is really saying that this whole fancy notation, it really says that you can take smash products of spectra, it's metric, it's associative, etc. And actually maybe the correct analogy to think about this is the analogy with respect to the tensor product in abelian groups, right? Tensor product of abelian groups. So because that's the analogy one uses in order to inherit plenty of algebraic structures, in a lot of algebraic concepts in the classical case of abelian groups to spectra. So you can basically take many definitions you have in classical algebra, in ring theory, etc., and then replace all occurrences of tensor product with smash product and get the corresponding definitions in spectra. So this is a common theme in homotopy theory. If you're wondering what I mean by this, for example, we can define what a ring spectrum is using the smash product. We say a spectrum is a ring spectrum if there is a map from X smash X to X that satisfies associativity and unitality conditions. So if you compare this with classical algebraic definition of rings, discrete rings, then you could define a ring to be an abelian group with a map from A tensor A to A that satisfies certain associativity and unitality conditions, right? That's how you could alternatively define what a ring is. So this smash product allows us to define these ring objects, for instance, in spectra. In the categorical language, these are just monoids in the symmetric monoidal category of spectra. That's what this is saying. That's the categorical language for this. Actually, there are a lot of examples of ring spectra. Many spectra that we encounter happen to be ring spectra, and sometimes even commutative ring spectra. The example I'm going to give to you is the example of the Eilenberg-MacLane spectrum. So this is a this is the analogous thing to Eilenberg-MacLane spaces in spectra, right? If you have a ring R, there's a spectrum called HR, the Eilenberg-MacLane spectrum of R, which is defined by the property that all of its homotopy groups are concentrated in degree 0. So it only has pi 0, and its pi 0 is R, and the rest of its homotopy groups are trivial, right? Its homotopy groups are R concentrated in degree 0. That uniquely defines the spectrum, and this spectrum happens to be a ring spectrum because R is a ring, basically. Now, I must mention that, so for each ring, you obtain a spectrum, right? HR. And actually, through this, the category of spectra contains all the information about classical rings in itself. So the category of ring spectra really generalizes the category of rings, right? It contains all the rings, it contains all the maps between them, etc. In particular, if you take the algebraic K-theory of HR, that is the same as the equivalence definition of the algebraic K-theory of the ring R. Okay, now I'm going to start talking about trace methods. So I told you about how it was difficult to compute algebraic K-theory, although they were pretty important. They were difficult to compute. And to be able to manage algebraic K-theory computations, this ambitious and program, which spanned over a long period of time, was developed, and a pretty successful program was developed. It's called the trace methods. The word trace comes from the fact that, remember, we had the general linear group involved of the ring was involved in the definition of algebraic K-theory. So you can apply the trace map to that, and that's where the methods involve that trace map, at least classically. So that's where the word trace comes from. So I'm going to talk about this program. In general, in trace methods, one works with what's called connective spectra. These are the spectra whose negative homotopy groups are all trivial. And the big result for trace methods is this theorem of Dundas, Goodwillie, and McCarthy. It's saying that if you have a map of connective ring spectra where the induced map on pi 0 is surjective with a nilpotent kernel, then there is a homotopy pullback square of this form that relates algebraic K-theory with topological cyclic homology. Now, I haven't defined what topological cyclic homology is. I'm going to do that in a second. But it is saying that there is what's called a trace map from algebraic K-theory to TC, and it fits into a homotopy pullback square. So, for example, okay, what does this tell us? It is saying that if you are in this situation, you have a map A to B. If you know the K-theory of B, if you know the TC of B, in order to obtain the K-theory of A, you just need to understand TC of A, and of course these two maps, right? So the idea is that it reduces algebraic K-theory computations into TC computations. That's the point of this pullback square. So you often apply this to the case where you start with this connective ring spectrum, and you apply the zero Postnikov section functor, right? And this is same as in classical homotopy theory, where you can kill all the homotopy above degree 0, right? And you obtain an Eilenberg-MacLane spectrum, because now when you kill all, you have something connective, kill all the homotopy above degree 0, you get something whose entire homotopy is concentrated in 1 degree. So this is the Eilenberg-MacLane spectrum of pi 0 of A. So you get this map. So if you take the K-theory of this guy, right, this is a ring spectrum, but as I told you before, the K-theory of this guy would be just K-theory of pi 0 of A, right? So often So in this situation, you would have to know the K-theory. If this is your B, right? This is your A, this is your B. Then you would just know the K-theory of that classical ring, TC of that. And then if you know the TC of A, then you would have the K-theory of A, right? That's the situation where often, not always, of course, but this trace method gets to be applied. And that's what we do in our work too. Okay, so topological cyclic homology. In order to define topological cyclic homology, I need to define topological Hochschild homology because that's what's used in the definition. I must say that, of course, I mean, TC, the point is that TC is more approachable than K-theory, but K-theory being so complicated, TC is also relatively complicated. Okay. So to define topological Hochschild homology, actually, we can just start with the definition of Hochschild homology, which was there before THH, topological Hochschild homology. We can start with the definition of that in the case of classical rings, and you can start with that definition, replace all the rings with ring spectra, all the tensors product with smash product of spectra, and you obtain the definition of THH. Right, so you get this simple bar construction, which is a simplicial spectrum given by x to the power s plus 1 at simplicial degree s, right? You get this x smash powers. The phase maps are given in this way. The first phase map here, for example, would be given by multiplying these two, right? And then second phase map would be given by multiplying these two. Third phase map, you do something funny. You apply a cyclic permutation to this level. You move this x to the right, this x to the right, and this x all the way to the front, and then multiply first two, right? That gives you your phase maps in your simplicial object. And the degeneracies are given by inclusion of the unit. And now, just like the way you can start with a simplicial space, apply geometric realization, and you would obtain a space, you can, with a simplicial spectrum, right, apply geometric realization and obtain another spectrum. And that's what you do. You apply geometric realization to the simplicial spectrum, and that gives you your THH. And the homotopy groups of the THH spectrum is your topological Hochschild homology groups. So this definition of THH is due to Böckstedt, and this was actually pretty hard to do back then because there was no category of spectra with a nice smash product, so that was really difficult work to define this in the first place. And the goal was to compute algebraic K-theory. That was what's inside. And after making this definition of THH, Böckstedt makes this famous computation of topological Hochschild homology of FP. And these groups are given as a polynomial algebra over FP with a single generator in degree 2. This is saying that these groups are trivial in all odd degrees, and then they are FP in all non-negative even degrees, right? And is trivial in negative degrees. So Böckstedt does this computation, and this is a very important computation because if you look at the definition of THH, you're smashing spectra, right? So smash product of spectra always depends on the stable homotopy groups of spheres, right? So a priori, this result depends on stable homotopy groups of spheres, and this one may expect this to be extremely complicated. But although the computations are really complicated, at the end you get this very simple result, and that's one reason why this result is important, and somehow like THH is good because you start with something so complicated, and in many cases you get pretty manageable answers. So that's some pretty surprising fact about topological Hochschild homology. And that's one reason why this is, such an important result. Okay, there's more structure on THH. You can apply cyclic. One can apply cyclic permutation of order n in simplicial degree n-1. This says that there is a C1 action in degree 0, which means no action. C2 action in degree 1, a simplicial degree 1, which is given by the switching these factors, and a C3 action given by the cyclic permutation of order 3 by switching the elements to the right and then the last one to the front, as I was telling you. So this Cn action, all these Cn actions compile together to give us an S1 action on THH. So there is a circle action on THH, and this is where the word, topological cyclic, the cyclic in topological cyclic homology comes from, because the definition makes use of this cyclic action. Okay, so I'm going to define topological cyclic homology, but to do that, first I need to give you a little bit more notation. So this is the definition of the Tate construction of a G spectrum with respect to the group G. So if you take homotopy orbits, and this denotes the homotopy fixed points of the G spectrum A, there is what's called a normalization map from orbits to fixed points. That's always there, and the cofiber of this map is defined to be the Tate construction on G. If you compare this with the classical case, if A was a discrete G group, G module, say, and G was a finite group, then the normalization map would be given explicitly in this way, right? From orbits to fixed points. But there's a way of making this categorical. There's a way of making this work in the setting of spectra too. And to define topological cyclic homology, one needs to define what is a cyclotomic spectrum. I use the Nicolas-Schulze definition. So the definition of topological cyclic homology and cyclotomic spectra, these are due to Bergstedt, Hsiang, Madsen from 1993. And the goal again was to study algebraic K-theory. And these definitions got significantly simplified with this recent work of Nicolas and Schulze. This is just from 3 years ago. What Nicolas and Schulze did is that they gave a new definition of topological cyclic homology and cyclotomic spectra, which really simplified the definitions of these objects, as well as computations one would do for these things. For instance, the older definitions were making use of what's called genuine equivariant homotopy theory, and the newer definitions actually completely avoid genuine equivariant homotopy theory, and they use what's called naive equivariant homotopy theory, which is much simpler. And the definitions themselves are in general simpler too. Okay, so in this case, a cyclotomic spectrum is an S1 spectrum with S1 equivariance maps from itself to its Tate construction for each prime. That's what a cyclotomic spectrum is. And THH of X is a cyclotomic spectrum. So I already told you THH of X is an S1 spectrum, but this also says that it comes equipped with maps from itself to its Tate construction with respect to CP. CP here again denotes the cyclic group of order P, and one considers it as a subgroup of S1, okay? So one can do that. And now we're ready to define. So THH has these what's called Frobenius maps, 5 P's, okay? So now we can define the topological cyclic homology of a connective ring spectrum. So it is defined due to the Nicolas Chaucer work to be the fiber of this map. This is a theorem, and one can also take it as a new definition of topological cyclic homology. One can define it as the fiber of this map from the homotopy fixed points of THH to this product, which is taken over all prime numbers of where you first take the CP Tate construction and then take the homotopy fixed points. And this map is given at each prime. It's given by the subtraction of the Frobenius with what's called the canonical map. I already told you what Frobenius is, and then you apply the homotopy fixed points function to this map. And then the canonical map is defined in this way. You can consider the taking homotopy fixed points as first taking homotopy fixed points with respect to CP, and then taking the homotopy fixed points with respect to S1. You can kind of like, it's because S1 over CP is also S1. That's what it is. So this side is actually equivalent to this, and the fixed points always map into the Tate construction. Okay, that comes from the definition of the Tate construction. So you have that's the map can. It's obtained using this identification and then the map into the Tate construction. So there's one thing that's kind of intimidating here: the fact that you take a product over all primes, but you know, it's common in homotopy theory that you kind of want to work with only one prime, right? For example, if X is an HFP algebra, or all primes except P is invertible in X, let's say, then in such a situation, all the factors in here except the factor corresponding to P just vanishes. Okay, and this fiber sequence turns into this fiber sequence. Now, it's kind of nice because the left-hand side is actually a homotopy, is a homology theory that was already known and defined and studied. That's called the topological cyclic homology, negative cyclic homology. And on the right-hand side, this side also has an identification as the Tate construction on THHX with respect to the circle. And that's also has a name. That's called the topological periodic homology. So basically, TC becomes the fiber of a map between two homology theories that people already knew. Okay, now we're ready to define, okay, so maybe I should quickly summarize. Basically, this is saying that in order to calculate algebraic K-theory of X, you would want to calculate the THH of it, right? And then apply all these things and figure out what TC of X is. And now from that, and you would have a map from X to another spectrum. And from that, you would try to obtain, using the pullback square of Dundas, Goodwill, and McCarthy, you would try to obtain the algebraic K-theory of X. So there is this way of going from X to THH to TC and then algebraic K-theory. Okay, so now I can start the statement of our results. So I say, on the title, I say algebraic K-theory of THH of FP, but we actually work in the more general situation of a perfect field rather than just FP. So we work with a perfect field K. From now on, K will always denote a characteristic P perfect field. Perfect in characteristic P means Frobenius of K is an isomorphism. That's equivalent to Frobenius of K being an isomorphism. Examples of perfect fields: FP is a perfect field. All finite fields, all algebraic extensions of FP are examples of perfect fields. The reason we can use perfect fields is because THH of a perfect field, it looks a lot like THH of FP. Okay, it's also a polynomial algebra. So Buxted results basically generalizes from FP to perfect fields. That's why we are able to use to generalize to perfect fields in here. Okay, so I showed you a little bit about this relative algebraic K-theory. So relative algebraic K-theory of THH of K with respect to K in this situation would be by definition be the fiber of this map. And so this map is given to be the map from THHK to K, which kills all the homotopy groups of THHK. This is the map I was telling you about. This is the map that kills all the homotopy groups of THH of K above degree 0, right? So this is the map to zero Poisson-Markov section, and then the relative K theory is defined to be the fiber of this map. And this map splits, which says that the fiber sequence splits. So the algebraic K theory groups of THH of K are really the algebraic K theory groups of our base field K direct sum with algebraic this relative algebraic K theory groups. What happens is that trace methods allows you to compute these guys, right? Trace methods allow you to compute these guys, and that's what we do. We really compute these relative groups using trace methods. We do TC computations. And then these things, if we happen to have them, then we obtain the K-theory groups of THHK. For example, when K is a finite field, I told you Coulomb gives us these K-theory groups. So we do have these things in that situation. So from that, from our computation, we get here, and from Coulomb, we get this one, and we obtain the algebraic K-theory of THH of all finite fields. Okay, so this is the statement of our result, of our main result. It's saying that in degree 2 R+1, these relative groups are given by width vectors of length R over K. Big width vectors on a commutative ring actually are the Coffrey is the Coffrey lambda ring on that commutative ring. Okay, so Coffrey means it's the right adjoint to the forgetful functor from lambda rings to commutative rings. Length R means that we use some sort of a truncation of the big width vectors. Okay, we get some sort of a truncation of the big width vectors. And then the even groups are trivial. Okay. And well,
can I ask a question?
Yes.
Can you tell us what lambda rings are? Thank you.
Yeah. So these are the rings where you have some lift of the Frobenius map for each prime. So instead of having a Frobenius map, you have a lift of the Frobenius maps for each prime. These, for example, appear in topological K-theory too in an interesting way, because you have you look at vector bundles and then you have wedges of vector bundles and then all these like properties the wedges satisfy give you again lambda rings, etc. But these also often appear in algebraic K-theory computations too. So this is kind of interesting. I mean, the fact that we get this result is pretty interesting, is because if you look at like similar algebraic K-theory computations from the past, you realize that the answer is often not this simple. And it's surprising that we get such a simple, nice answer in here. This just comes out from the combinatorics of the spectral sequence computations we do. That gives us no idea why, no philosophical idea why we get these nice groups at the end with this very compact and simple definition. But it would be very interesting to know why one do get this simple answer in here. Like we have, our computations give us no philosophical answer. That would be really good to know. Again, as I was saying before, in the case of finite fields, this gives together with Coulomb, this gives us the algebraic K-theory of THH of finite fields. Okay, I'll start with a few applications of this result. The first application I want to mention is to the algebraic K-theory of K-theory of FP. So because FP is a commutative ring, when you take the algebraic K-theory of that, you obtain a commutative ring spectrum. Now you can take the algebraic K-theory of that commutative ring spectrum too. And this is actually an object that is of interest on its own. It's something that was studied before. For example, it's known that this spectrum knows about what's called the two periodic elements of the sphere spectrum in the homotopy groups of spheres and so on. So we look at these sequence of maps. So I told you that, trace methods, the big result is that you have this homotopy pullback square, which tells you that you can obtain K-theory from TC in these situations and so. But trace methods, sometimes you don't use that pullback square, but sometimes people just use the fact that there's a map from K-theory of TC and also a map from K-theory of, THH that factors through TC. Sometimes people just use this map and try to obtain information about the left-hand side by using their knowledge of the right-hand side. And so we look at these maps. You can go from K-theory of FP to TC of FP to THH of FP. And then apply the K-theory functor to that. And what we do is that we identify the right-hand side and we look at what can be said about the middle term too. And actually, we identify the middle term. We also compute the algebraic K-theory of TC of FP. This is kind of a side result that came out of our considerations. So what we do is that we show that TC of FP actually is same as the cochain complex on the circle with p-adic integer coefficients. We show that this is an equivalence of ring spectra. It is actually an equivalence of DGAs. And we show that using the Hopkins-Miller obstruction theory. It's not super surprising because if you look at the homotopy groups of the left-hand side, that's same as the cohomology of the circle with ZP coefficients. But we show that these are equivalent. And then it's due to N2-Gepner-Heller that it comes from theorem of the heart that the algebraic K-theory of the right-hand side is already known. It truncates. So that's how we get this result, right? So K-theory of this is K-theory of this, and due to N2-Gepner-Heller, this is K-theory of the p-adics. This tells us that this sequence is identified in this way, and the right-hand side we have a complete identification of the groups. And it's interesting to look at this. If you kind of look at this, you see that there are non-trivial elements here, which may possibly be detected from the known non-trivial elements in here. So you have like degrees where you have non-trivial elements in the same degrees. But we don't know. It's open and it's open to investigation to look at if these maps are really detected. These non-trivial elements are really detected through this map. Furthermore, one may ask if those are also detected through this map. There are interesting things there to think about. Another application of our main result is to what is called the fundamental theorem of algebraic K-theory. So I was telling you that algebraic K-theory is difficult to compute, but in the case of these polynomial algebras, you have this really strong result, which is called the fundamental theorem, which says that if you have a Noetherian regular ring R, then the algebraic K-theory of polynomials over R is same as the algebraic K-theory of your base ring R, which is kind of surprising, because it is known that if you would quotient out this polynomial ring with some power of x, right? If you get a truncated polynomial algebra, then that's not the same as the algebraic K-theory of that is not the same as the algebraic K-theory of the ring. So, but there is this result. So what we do, our result, in the meantime, says that this fundamental theorem of algebraic K-theory does not generalize to formal differential graded algebras with polynomial homology. So you can think about formal DGAs as a generalization of rings, right? And then if you take, but we show that there are formal DGAs with polynomial homology whose algebraic K-theory doesn't truncate this way. So let me make this precise. So a DGA is a chain complex with an associative and unital multiplication, and where the differential satisfies what's called the Leibniz rule. These are precisely the monoids in chain complexes under tensor product of chain complexes, right? That's what they're. So DGAs generalize rings. Take a ring, right? Just like every module is a chain complex, right? They concentrated in degree 0. You can take a ring, think about it as a chain complex concentrated in degree 0. That's the DGA. You can do more. Actually, you can take a graded ring, think about it as a chain complex where the degree I part of the chain complex is given by the degree I part of the graded ring. And imagine your chain complex has trivial differentials, right? So this graded ring just obviously turns into a DGA with trivial differentials, right? And these are what's called the formal DGAs. Right. So let's focus on this particular graded ring, right? Kx2, right? The graded polynomial algebra with a single generator in degree 2. This is a formal DGA. One can think about this, as I said, as a formal DGA, and use the fact that in spectra basically contains. Ring spectra contains all the DGAs too, not only all the rings, as I said before. If you focus on this particular ring spectra called HC algebras, these are the algebras over the Algebraic-MacLane spectrum. It's a commutative ring spectrum. You can look at the algebras over, right? Then if you look at these spectra with the structure of an HC algebra, that's same as DGAs. In particular, for obvious reasons, THH K for a perfect field, K, as I said before, precisely corresponds to the formal DGA Kx2, right? So when we say the algebraic K-theory of THH of K, that's at the same time the algebraic K-theory of this formal DGA with polynomial homology. Now if fundamental theorem of algebraic K-theory generalized to formal DGAs, then the algebraic K-theory of this gadget would be the algebraic K-theory of K. But our result basically identifies, so because of the discussion here, algebraic K-theory of this part is algebraic K-theory of THH of K, and our result precisely says that that's not same as algebraic K-theory of K. So it is saying that this polynomial algebra, this DGA with polynomial homology is not its algebraic K-theory does not truncate, or the fundamental theorem of algebraic K-theory does not generalize to formal DGA. Okay, so I was saying that we have a new identification of THHK as an E2 algebra. So to define what this means, I need to tell you a little bit about what it means, what these EN algebras are in spectra. So I told you in spectra we have ring spectra. One can also define in a very similar way what a commutative ring spectrum is. And of course, in the classical case, there's nothing in between in the classical associative rings and commutative rings. But in spectra, you have all these things in between. And actually, in a lot of situations, like not only in spectra, but in many other situations, you have these EK algebras, which somewhat sit between ring associative rings and commutative rings. I mean, if you're familiar with operands, these are just algebras over the n operand in spectra. That's the correct way to think about it. If you're not familiar with that, then E2 ring spectra could be, for example, considered as a ring spectrum whose multiplication is commutative up to homotopy, and this homotopy is asked to satisfy a coherence condition. And as you increase these coherence conditions, then you go from E2 to E3 rings and so and so. And and so we already know THH of K. THH of K is actually a commutative ring spectrum, right? Because K is a commutative ring spectrum, it comes from the formality that THHK is a commutative ring spectrum. So in particular, it's an EK ring spectrum for each K. So we immediately have this identification of THHK as an E1 algebra. So on the right-hand side, what you have is the loops on the 3 sphere. Like this is just space, you can apply the infinite suspension functor and you obtain a spectrum. Now, because there is the loops functor in here, it's a loop space. You can compose loops, right? That gives you a product in here, which turns this whole thing into an E1 ring. So this whole thing is an E1 ring. And because of Snate splitting, we know that this is the free E1 ring. And from Buxted's results, because it's the homotopy groups of this guy is free, you know that this is also the free E1 ring on a generator in degree 2. So these things are known to be the same. It's pretty immediate from the things we already know. But there is also this interesting thing here. If you look at this carefully, this thing also happens to be E2. It comes from the fact that S3 is a group, is a topological group, because of the quaternions. Now, because this is already E1 and you have loop it, this whole thing becomes E2, right? So the right-hand side is E2, left-hand side is commutative, therefore E2 in particular. Does this also agree as E2 algebras? And we say yes. We show that this actually can be promoted to an E2 equivalence of ring spectrum. So this gives us a new identification of THH of K. Because S3 is a topological group, this is E2. So we proved this using Basra-Mendel obstruction theory, which allows you to do classifications through Postnikov towers. So you do certain undercooling cohomology computations, and which allows you to classify Postnikov towers of these two things, and we show that they are basically the same. That's the idea. And why did we need this E2 result for our algebraic K-theory computation? So we're going to compute the algebraic K-theory of THH of K. For that, we need to first understand the THH of K, right? In particular, we had to really know among certain other things provided by this theorem, we had to know, for instance, the THH groups of THH of K as a ring. So this was already known as a module, but we needed to know the multiplicative structure on the THH groups of THH. And we obtained this one. So this was already known for the case when K is a finite field and for primes larger than 3, but we generalize it to all primes and all perfect fields. So why did we need this multiplicative structure because, so we had to understand this fiber sequence, right? There is a spectral sequence that starts with THH of THH and then gives you the homotopy groups of the homotopy fixed point on THH of THH. They're called the homotopy fixed point spectral sequence. That's a multiplicative spectral sequence, and we had to use a multiplicative structure. In order to use the multiplicative structure, we had to know the ring structure on the THH groups of THH of K, right? So that we exploit that. And we needed the E2 identification here for that reason. And then similarly, the Tate construction, there is a spectral sequence that's multiplicative. We had to know the multiplicative structure on the groups of this one. Another result, conceptual result that goes into our computation is our use of what's called graded ring spectra. So I will not have time to get into that, but we show that THHK is also what's called a graded ring spectrum, and we show that there are splittings on the topological negative cyclic homology of such things, but yeah, so I will not have time to get into that, so I better stop here. Okay, yeah, thanks for listening.
So let's thank Ozgur. That's a very nice talk. Are there any questions or comments?
Hi, Paul, by the way.
Hey, I have a question. I have a couple questions, actually.
That's great.
So is the E2 algebra structure that you found on THH of K, is that the same as the underlying E2 structure of the polynomial algebra on a generator in degree 2 over HK?
Is it formal? That's what you're asking.
I think so, yeah.
Yeah, it is formal.
Okay.
We actually show that there's a unique E2 DGA with the given homology.
Cool. Okay.
So it is a formality result. Yes.
I was interested in this comment that you made about different THH of different deformations, formal deformations of K. And I'm wondering, do you know what you get if instead of starting with this generator in degree 2, you start with the generator in degree 4 or something like that?
Yes, that's something we're looking at. But there are funny things going on there. For example, what we did is I used the fact that S3 is a group, right? Mm-hmm. And some, it's just happened to be the case that S5 is not a group. You can't go up and these spheres are not groups. Otherwise, you have just S3, S1 are groups. So what can you do? Well, there are certain things. For example, if you localize at a prime, then many other spheres also become groups. There's that result. So you don't just have S3, many other spheres also are groups. So so you get this that allows you to get the algebraic K-theory of these formal DGAs with a generator in different places.
I see.
That's something we're looking at, which also works. So that's like a future project of ours, actually. Actually, we also have the truncated homology, DGA with truncated homology in degree, say, n, right? Mm-hmm. So you just kill x to the power 2. It's basically exterior algebra on a single generator. So so we can do that. It seems like we believe in a future work we can. But like not every, we have most of it, but we just didn't have time to check all the details. Also, you can map these like polynomial algebras to one another and look at those. Mm-hmm. That also gives you some information, also recovers the polynomial DGAs with polynomial algebra with generator in like higher degrees. Mm-hmm. But we don't know how to do all the degrees at the moment.
Okay. So you actually need to use the group structure on S3 to do this.
Oh yeah.
These computations.
Yeah.
That's really interesting.
Yeah, that's really interesting. And that's it's very pleasant to have that this thing is E2, because you see, I didn't mention it, but when you have these smash splittings in THH is symmetric monoidal, right? So we're going to compute THH of this, and it's great to have the smash splitting whenever you can. And then, but the problem is that you want that splitting to respect that splitting to be a splitting of E1 algebras at least, right? So that you can input the ring structure and homotopy into the spectral sequences computing this guy.
I see.
Right, so because if you have an E1 splitting, then the THH of it will split just as a spectrum, but you want an E2 splitting so that the THH splits as an E1.
I see.
So this is beautiful that we have the E2 splitting, and this is E2, but yeah.
Okay.
Can I ask a question about the E2 splitting?
Yes, of course.
So one way to obtain this form of THH of K, I think, comes from sort of knowing that H of P is a Thom spectrum of a double loop.
Yeah.
But that map is actually a triple loop map, which would make THH, which would give some structure of THH as an E2 ring already. So I wonder if you can obtain this result. It sounds like you did something different to obtain this THH as an E2 ring, but like we already know it's an E2 ring because this Thom spectrum map is a triple loop map.
Yeah, we know that it's an E2 ring.
But are you saying that we just didn't know that it was an E2 ring in this way, or?
Yeah, we didn't know it was an E2 ring in this way. It's a double loop map, so.
It's a triple loop.
Oh yeah, but yeah.
HP infinity thing again.
Yeah. But we didn't know that it was an E2 splitting in this way. Yeah. The one that comes from the E infinity structure of THH of K.
So are those different then? Are those different E2 structures? The one that.
As long as your E2 structure is an HK algebra structure, we show that they're all the same. Sorry, who is speaking? I can't see.
Oh, sorry, this is Ishan Levy. I don't have my camera on, sorry.
Oh, okay, Ishan Levy.
Yeah.
Okay.
Okay, so you're saying that, but I wonder if there's a way to directly see that from this Thom spectrum construction.
Yeah, I don't know. As far as I see, there's none. But...
I have another question, Ozgur.
Yes.
You said that TC of FP can be identified with the cochains on S1 with coefficients on ZP, right? I was wondering if there's I don't want to say dual, a pre-dual version of this statement in terms of coalgebras. Okay,
let's think of it. So what would be the S1 of ZP? Is that what you're asking? Sorry, you can take the homology of S1 with ZP. Is that what you want to do?
I'm saying, can you make sense of the left-hand side if you put chains on S1 on the right-hand side using one of these versions of THH and TC?
Yeah. Okay, let's say TC. Yeah. Never thought about it, to be honest.
Yeah.
The one reason never thought about it is because this S1 action on co-THH is not even studied. So no one said anything about it.
Why is that? I mean, I think you can make sense of it, right?
Yes, you should be able to make sense of it. But you see, like the reason people studied the S1 action on THH was because of trace methods, right?
Right.
And we don't so far know how to go from code THH to algebraic K-theory. Another reason is because for that, you would want to look at the S1 action, you would want to look at the Frobenius, what would be the corresponding thing. Definitely interesting things could be said there, but it's just that the study of code THH is at too early of a stage, I believe, that it wouldn't allow us.
Yeah.
It wouldn't allow us
It's
to.
not relevant for K theory a priori, right?
Yeah, it's like, I mean, I'm saying it's one may definitely want to think about that, but it's not studied yet. And now, okay, let's say it is already, we have something, right? Then you're asking, then maybe the corresponding code TC thing should be the code TC of FP. One would want it to be the homology is a coalgebra. Yeah, I mean, that may be true. I don't know really, but there are things. Yeah, what is the correct notion of code TC in the first place? For example, you say code TC as a coalgebra, right? Code TC. I mean, does code THH has a coalgebra structure? We still don't know. THH is an algebra in an obvious way whenever you start with a commutative ring spectrum.
Yeah. I think the answer is, I mean, I understand the DG case, and in that case, everything works out, and you should have a ring structure as well. Oh no, sorry, a co-algebra structure. Yeah.
Yeah, I mean, code THH, as far as I know, Brooke, Anna Marie, and a few other people, I'm not sure. They're working on showing that code THH is a coalgebra, but right now we don't even know if code THH is even a coalgebra.
I see. In the DG case, I mean, I've noticed
in that situation, but there's an S1 action.
Yeah.
There's an S1 action, but what do you do? How do you define TC in that situation?
Right.
So it's a little bit of a question of a feature we don't know about.
Yeah. Okay.
That's my point. But it's definitely interesting. I mean, because you're referring to our duality result, right? Because co-THH dual is dual, and then co-chain dual is chain. So does that make TC of FP to it? Yeah, that's definitely an interesting question.
Okay, are there any other questions or comments?
I put a comment in the chat. There's this paper of Blumberg, Cohen, and Schlichtkroll, where they explain how to compute THH of a Thom spectrum.
Yes.
Right. So I'm wondering if so they have this thing where if it's like E3, then you can say that the Thom spectrum is just they have some particular formula for it. It's just I'm wondering if that's actually an identification of algebras, if there's some algebra structure that respects.
Yeah, maybe possible to do it through Thom spectra too.
Because then I think that would be a result if
yes, there may be a way of obtaining this through, but as far as I remember, it's also due to work of Mao, recent work of Mao, what he was talking about, and also actually there's another thing. Nicolas and Crosse also has a paper where they look at they give a new proof of this Böckstedt periodicity, right? Where they kind of like explicitly identify THH of K, but by using this Thom spectrum property, right? And that the problem is that whenever you go through that, you end up getting an E1 identification of THH of K. That's what I've been seeing. I don't know, maybe you can see another way. I'm not
Yeah,
saying
but
that,
I'm saying that so there's this map from so there's a map from, but that actually gives you the THH as an E2 algebra, because there's actually a way to deloop the map from like, it's a triple loop map, not a double loop map. So when you
yeah.
you should get it as an E2 algebra. So I'm just wondering if their results.
Yeah, as far as I remember, that just gives you the.
It looks, it's only stated as a spectrum. I think they only say that like there's an equivalence. But
yeah, because they don't have the, they just do it in the spectrum case.
Yeah.
As far as I remember, like as far as I see, like I went through all these things where they use that Thom construction to obtain these identifications. And as far as I could see through that, you reduce down to an E1 identification of THHK. I mean, it would be good to look at it definitely later, but that's what I saw. If there is a way of using that triple loop map and then try to obtain an E2, it would be interesting to know that. But as far as I saw,
okay,
that's what we were able to get.
Thanks. Is that statement that if it's a triple loop map, then you get an E2 description of the Thom spectra? Is that actually proved? Because they say in their introduction, like, we expect this to be true. Does someone else prove it, or?
Oh, I see. So you're saying that was actually conjectured or something in their introduction?
Yeah, but also, this paper is 12 years old, so maybe by now someone has proved that statement.
Yeah, there's Mao's work, for example, like that's also interesting. There's Mao's work where he does use the fact, he shows that you can also do that Thom spectrum identification as for perfectoid rings too, not just for FP. Okay. He starts with that, but again, you can only go up to an E1 identification of THH of K. That's the thing. And why does that happen? I think you get triple loop map, but that gives you an E2 identification of FP. I don't remember exactly how the procedure worked, but so basically what you say is generalized to perfectoid rings by Mao Zhuang. Sorry, I don't remember his name, but he's a student of Matthew Merrill. He can only go up to an E1 identification of THH by using that Thom spectrum method. I mean, of course, if you can do this to an E2 identification of THH of K, that would be great, because you will be able to also even generalize our results to perfectoid rings. If you combine it with Mao's result, possibly you would be able to generalize to perfectoid rings, and that would strengthen Mao's result from an E1 identification to an E2 identification. But yeah, but I can't really tell. As far as I saw, I went through that route, and as far as I could see, there was only an E1 identification. If you know, of course, that would be great.
Okay. So if there are no more questions or comments, let's thank Ozgur again.
Thank you very much. Thank you very much. It was a pleasure.